So we could relate the microcanonical and canonical partition functions to one another through entropy. And by doing that, that allowed us to relate entropy back to probabilities through the Shannon entropy equation. We could also relate the canonical partition function to previous results we've seen previously. And so, for example, let's now consider a system comprised of n distinguishable particles, and that these particles in their J state, let's say they have n energies, such that the internal energy of the J state would just be equal to epsilon 1 plus epsilon 2 plus dot 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 epsilon n. And we could write this as a summation of epsilon sub L from L to n. And so the partition function Q would just be the summation of the exponential of negative uj over kBt, which is equal to the summation of the exponential of another summation, epsilon L over kBt. Okay. All right. And so this summation, we could expand it out so that we have exponential of negative epsilon 1 minus epsilon 2 minus dot 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 epsilon n over kBt. Because we're dealing with exponentials, and we have this sum in the numerator here, we could write that by splitting it up into different exponentials. Epsilon 1 kBt times exponential summation of exponential negative epsilon 2, and then dot 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 multiplied by another summation exponential negative epsilon n over kBt. Okay. All right. We could write this product of exponentials in a more compact form like this. Q is equal to the summation of the exponential of negative epsilon j kBt, all of that raised to the n. And so this partition function, this form of it, is actually identical to the partition function we first derived back in Module 5. Okay? All right? Of course, we could also define the partition function, the canonical ensemble partition function, for a system of indistinguishable particles. To do that, we just divide by n factorial. Epsilon j kBt raised to the n. And then, just like in Module 5, we could also define the single particle partition function. Where just lowercase q is equal to the summation of the exponential negative epsilon j over kBt. And so in summary, with the canonical ensemble, with its partition function, we could relate this back to concepts that we previously derived using other thermodynamic approaches. And the fact that we're getting consistent result means that we're still describing the same end results. But now we have a different framework which starts exclusively from the microscopic viewpoint.